Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Hopefully you guys have been having a good week. Let's actually jump in. Let me share my screen. Okay, so, all right, that looks good. That looks okay. Let me make sure that I can see the chat and everything here. Okay, all right, we look good. Let's actually jump in and get started. So we actually started the topic of improper integrals last time, even though we didn't really get to do anything with it or do much, but we spoke about some important pieces that go into it, and the rest is actually very computational. So let's just do a quick recap before we move on. So improper integrals, what are they? Well, improper integrals are referring to definite integrals, right? So we have an integral from a to b of f of x dx, and we actually want to be able to integrate. Some people are still checking in. We actually want to be able to integrate from a to b of the function f of x dx. Now we would know that we could set up some sort of Riemann integral situation going on with what we learned from Calc 1. Okay, find the antiderivative, plug in the top number, plug in the bottom number, etc. However, it turns out that there are cases in which this just simply does not work because for the fundamental theorem of calculus to apply, we made certain assumptions about the function. Two of these important assumptions are the function is continuous. This allowed us to use the mean value theorem, and also that the interval was of finite length. We could just take a length from a to b, we can cut it up into pieces, n pieces. The width of each of these was delta x and blah, blah, blah. So we know all of that. Okay, so these were the assumptions. Now, when you're looking at an improper integral, what we're pretty much looking at is a kind of integral where one or both of these assumptions just aren't true. So either our function is not continuous on the interval, or the interval itself is not of finite length. It's not something that it kind of makes sense to dissect it in the way that we've been doing it. And that leads to something called an improper integral. So basically an improper integral, how you want to think about it, well, it's an integral from a to b of f of x, such that either f is discontinuous at one or more points. So the mean value theorem doesn't really work as well as we thought it would, at least not on the entire interval, or the lower limit is negative infinity, or the upper limit is positive infinity. And all of these are really sort of and or situations. So you can have any one of these things happening makes the integral improper. However, you can actually have all of these things happening or some of these things happening, okay? So whenever you're in one of these situations, you have infinite limits on your integral, or your function itself is discontinuous somewhere on the interval, you get what's called an improper integral, right? It's kind of a guy that doesn't fit in with the assumptions we made in the fundamental theorem of calculus. So we have to be very careful. The approach for this, we actually do have an approach, which I summarize here, is first for you to identify the bad points. Identify the points that don't make your function continuous. Identify whether or not you're in an infinite interval, and so on and so forth. So you want to first identify what all the issues are that would make the integral that you're looking at improper. The next step is to actually break up the integral, right? So we had properties that tell us how to break up integrals from Calc 1. We can apply those here. And essentially what we want to do is to break it up such that these bad points are exposed, and we will have one of them per integral, because the third step is to actually use limits to approach the bad points. So basically, because something bad happens at this point, we can't really assume that we're there. So what we do is we take a limit to get close to there and see what happens. And so because of that, we need only one side to actually be bad at a time, because you can't have a limit that is approaching two different things at the same time. That's not how limits work. So we have to break it up so that there's only one bad point to deal with at a time, and take a limit to approach that point. And so we go through, we compute all these limits, and we add all the answers together. And if it makes sense to add them together, we say the integral converges. So we can say the improper integral converges to this value, and it's going to be the sum of all these limits. And if this does not happen, meaning that you get limited equals infinity or negative infinity or does not exist, we say that the improper integral diverges. So there are two situations. So converges sort of means this improper integral has some sort of answer that is equivalent to the kind of answer that I could expect from what we did in Calc 1. Whereas if it diverges, then this is not the case. Okay, so what we're going to be, I'll talk a little bit about that situation as we go on, but for now, what I do want to do is focus on how you'd actually go about computing improper integrals, because you'll need to know how to do that for your quiz tomorrow. So the first example we actually already did. We have to identify what makes an improper integral improper. So if you're looking at the integral from 1 to infinity of 1 over x dx, there are possible issues are if I divide by 0, so if x is 0, that's bad. However, I'm on the interval from 1 onwards, so that's not an issue. However, the upper limit is infinity. So we have an interval of infinite length here, right? So it's kind of like you want to find the area under the curve starting at 1 to forever, right? How do you actually go about doing that? Well, essentially you take a limit to approach the infinity. So you assume that I'm really looking at an interval from 1 up to some number n, and what I do is I push that n further and further away from me, going off to infinity, and see what happens, right? So we're kind of using a limit to approach the bad point. Moving on to the next example, you'll notice that this one here has a bunch of issues, right? So what are the issues with this that doesn't make this jive well with the fundamental theorem of calculus? Well, the lower limit is negative infinity and the upper limit is infinity. And there's a point where the function is discontinuous in between these two. So negative infinity, infinity, and 0 were the bad points. So what we had to do is we had to break this integral up. So the first breakdown is what we had here. But we realized that that didn't really work because I have two issues on each integral. Both 0 and infinity are issues. I can't have a limit approaching 0 and infinity at the same time. So what that means is I have to break it down even further. So we pick a random point in between 0 and negative infinity, and another random point in between 0 and positive infinity, which here we chose -1 and 1 respectively. And we can end up breaking this integral up into 4 pieces. And so we could actually approach each individual point with a limit. Okay, now we'll talk about how I did actually rush through sort of computing these guys before, but essentially what you're going to do is you think of each of these limits as separate things, and the goal is to see if they all converge. Now, every single limit has to converge. You can't consider that one would cancel out another, for example. So if one limit gives you positive infinity and the other limit gives you negative infinity, you cannot assume that the infinities are the same and they'll actually cancel each other out. That's not true in general. There are different sizes of infinity. That's something that you'll worry about in set theory. But as long as each of the limits converge to a finite number, then we can add up all these finite numbers and we can actually interpret that as something meaningful, namely being something like the area under the curve or something very similar to that. So that being said, let's actually move on to this one. So in this example here, in the first example, the goal is to just identify the bad points and break them up, right? At this point, don't worry about what the final answer would look like. So go, what do you think for this one?
The bad point is x equals 0.
Okay, so you identify the bad points, x equals 0, because you divide by 0. Our f of x is 1 over x, and it's undefined at 0. Okay, anything else? No, that's it, right? Nope. So how do you deal with that? Now knowing that it is 0, what would you do? I'll decide.
You would break it up into the integral from -1 to 0 plus the integral of 0 to 1 of 1 over x dx.
Right. And what you can do at this point is you can actually use limits to approach the 0. So we can take the limit, say, as n approaches 0 of -1 up to n. And in fact, I can know that I'm approaching 0 from the left side, take a completely different limit, say m approaching 0. It'll approach 0 from the right side. Right, so if the limit exists, you don't really have to worry about the one-sided limits, but remember, the limit from the left doesn't necessarily have to be equal to the limit from the right, so we have to be aware that we have to be careful here. Do we understand, first of all, let me make sure before we move on, do we understand why it's from the left and from the right in the way that I wrote down?
Is it because it's -1 to 1, so like the -1 is from the left and then the 1 is from the right?
Yeah, well, if you look at the interval here, for this one, it was from -1 to 0, right? And then for this one, it was from 0 to 1, right? So here, if I'm approaching 0, we're coming from the left, right? Whereas on this integral, if I'm approaching 0, I'm coming from the right. Right, so you can just picture it as an interval and just see, oh, 0 is the bad point. If 0 is the end point of this interval, would I be coming from the left or from the right? There are situations in which it can matter. If your limit would exist from either side, then it won't, you would get the same answer, but it's possible for it to exist from one side and not the other. So if you want to be super pedantic, you do have to identify what side you're approaching from. And it's just a matter of just look at the interval. If it's on the upper limit, then you're approaching from the left. If it's on the lower limit, then you're approaching from the right. Unless the bad point is infinity, in which case you don't really have to say anything, right? Because you can't approach infinity from the right, right? So obviously if you're approaching infinity, it's from the left, so you don't even have to write it. And obviously if you're approaching negative infinity, it's from the right, so you don't need to denote that. But for any finite limit that we're covering, you might need to be aware of what side you're approaching it from. And yeah, this one.
So 2 would be the bad point?
Okay, it's a bad point. X equals 2, because that causes a division by 0. Everywhere else, this function is fine. The interval is not infinitely long, and so 2 is the only point that we have to worry about. So yeah, so this is I, and how would I break that down?
So you do the I equals the limit from 0 to 2, and then of the integral, and then plus the limit from 2 to 3 of the integral.
Okay, throw in the limits. How would it look?
So if you do the limit, n would be 2 from the left of the integral, and then plus the limit of m to 2 from the right of the integral.
Okay. Now, how you proceed from this point is very similar to what we've been doing, so I'm not going to harp at it right now. I want you guys to get used to the idea of breaking these things up and applying the limits. What do you think here?
The bad points are 1 and -1. X equals 1 and -1.
Right. So? How do you break this up?
So you separate it from -2 to -1, and then from -1 to 1, and then from 1 to 2.
Okay. Does that work?
No, because we have both bad points in the middle integral.
Okay, so the middle integral doesn't really work because there are 2 bad points on that. We only want 1 bad point, right? So this one has 1 bad point, that one has 1 bad point. Having 1 bad point is fine because the limit can approach that point. We can't have the limit approaching both 1 and -1 at the same time. So the middle integral has a slight issue, but you just continue. You break that down even further. So, and again, you can pick any random number in between. So let's say we chose 0. So one bad point here, one bad point there, one bad point there, one bad point there. So, all right, we're broken it up. All the bad points are exposed, and there's only one bad point per integral. So we are good. Maybe tell me how the limits would actually be set up here. So go in and apply the limits.
Wouldn't the first one be limit as n approaches -1 from the left? Then the next one would be m approaches -1 from the right. And then I don't know what letters you like to use, but the following one would approach 1 from the left, and the one after that, the
M
last one.
approaches -1 from the right. Yeah, I mean, the variable you choose here doesn't really matter, whatever. P. P approaches 1.
1 from the left, yeah, and then the next one would approach 1 from the right.
And let's hope we have space here. Plus, say, the limit of Q approaches 1 from the right, of Q up to 2. And at this point, our integral is 1 over x squared minus 1. Right. This one.
We wouldn't need to separate it, right? So it would just be the limit as n approaches 5 from 3 to n.
Approaching 5 from what side?
From the left, right?
From the left. Yeah, you don't need to break this one up. There's only one bad point, and it's already exposed. The 5 is bad.
The bad points are negative, and then negative infinity and infinity.
Right, so then?
So then you could pick any point, right?
Yeah.
So then I would just do the limit from negative infinity to 0, and then 0 to infinity. So then the limits would look like limit from n to 0. Oh no, negative infinity from the left. Oh, you shouldn't have to write that. And then the limit of n to infinity.
So this is e to the minus x squared dx plus the integral from 0 to, let's write down the limit. Let's use n. Yeah, okay. So the breaking up, I think we're okay with that. So any questions on any of these breakdowns and how we set up the limits? Questions on that? No? Okay, let's actually go and fully compute some problems here. Now, you might be wondering, why would we need to compute this? And this is something that we'll explore a little bit, not a lot, as we go on. But it turns out that some of these guys, you might say, oh, come on, an infinite limit, like I'm never going to have to deal with that in reality, am I? It turns out actually you are. Like these improper integrals, it's not just something that we're exploring for fun. It's actually very important and very useful to compute them in some situations. And I'm not just talking about mathematically theoretical, abstract situations. Like you really need these guys in applied mathematics and applied engineering and applied sciences and all that good stuff. I mean, this integral here, does anyone know some sort of context that it might relate to? And this is kind of a question thrown out in the dark, but just in case like with a slight modification on this particular integral, for example, g, does anyone know what context that would come up in, or it's very vague? Have any of you guys taken statistics?
Yeah.
Yeah, so you remember the normal distribution from statistics?
Yeah.
Yeah, it turns out that the normal distribution is a curve like e to the minus x squared, except the mean and the standard deviation are constants that you put on it. So it's like minus x minus mu all squared over 2 sigma, e to the minus x minus mu all squared over 2 sigma. That is actually the graph of the normal distribution. And it turns out that you can find the probability by finding the area under the normal distribution. And so that's an integral. And so when you actually did statistics and you looked up that table of where, you know, you're looking for the z-score and you want the area to the left or to the right, where did those numbers come from? It came from us doing an integral, right? But when you're in statistics class, no one tells you that. So it turns out that these guys are actually very useful. It's not like something that we're just playing around here. These integrals are important. They show up in real life and they show up in non-theoretical settings, like actual things where we can compute things in the real world. So just because there's an infinity in there or your function, it's impossible to live at a certain point, don't think it's any less useful. Another thing that you would have integrals of infinite length, things like when you're doing Fourier series and differential equations, these guys actually come up. So just because infinity is in there doesn't make it nonsensical. It's actually pretty applicable. So I just wanted to point that out. So in Calculus 2, we really focus on just the methodology of computing things. But I do want you guys to appreciate that it is useful, the things that I'm teaching you how to compute. But let's actually go on. Let's actually fully figure out whether something is divergent or not, right? So we are going to fully work out a problem. I believe this is one that we already set up. So we're looking at 1 over x squared, the integral from 1 to infinity dx. Okay. So I would identify this as an improper integral. And so the bad points are 0 and infinity. However, 0 is not in the interval I'm considering, right? So I'm only on this number line, I'm only, let me do this in a different color. So on the number line, 0 is a bad point, 1 is a bad point, and I'm only on 1 to infinity, right? So 0 is a bad point, but not on our interval. So we don't care. Okay, so the only bad point according to this integral will be the infinity. So what we would do is we'd set up a limit. Say n is approaching infinity, going from 1 up to n of 1 over x squared dx. Okay, now once you do that, there's nothing to break up in this situation. What you actually do is you actually compute the integral, forget the limit. So what you do now, once limits are set up, ignore them at first. And compute the integrals. Which good, we're all experts at computing integrals now. We know all the techniques to compute all the integrals. You know what I mean. In Calc 2, we know all the techniques you'll need to compute all the integrals. So that actually comes into play. We'll actually need to be able to compute this integral. So as far as we're concerned, n is just some constant, and it's a constant that is fine to plug in, right? So we're just thinking of n as a number here, right? So you think of it as some regular definite integral where on the interval, everything is dandy on the interval from 1 to n. So what we would do is we'd leave the limit, just ignore it at first. And I'm going to evaluate the integral. So I want to integrate 1 over x squared. What is the integral?
Negative 1 over x.
Right, so this is minus 1 over x, and I'm going between 1 and n. Now, n is just some number that I can plug in. It's not a problem, so I plug in n into the x, minus, which becomes a plus, plug in 1 into the x. So I apply the fundamental theorem of calculus, the whole shebang. So I leave the limits alone for a while, just worry about the integration part. Now what you'll realize is that I end up with this limit, right? So I end up with the limit as n approaches infinity of minus 1 over n plus 1. And so it's a limit problem. I just take the limit of that, okay? So once integrals are evaluated, then take the limits. Okay, so this limit right here, limit as n goes to infinity of minus 1 over n plus 1.
It's 1.
It's 1. So what I would say is the integral from 1 to infinity of 1 over x squared dx is 1. The language that you would use is the integral from 1 to infinity of 1 over x squared dx converges to 1. Now, what does that actually mean? How is that actually interpreted? It turns out, we'll deal with this example soon. It turns out, one interpretation. And it's an important interpretation. Basically what I'm saying is, okay, so if I have the graph of 1 over x squared, which we know looks like this, and we know looks like that, and you were to ask me, if I were to find the area from 1 onwards to infinity, forever, right? Like, don't stop, the right hand, like just find the area under the curve from this point to the right, going on forever. It turns out that the area here is finite. So there's an infinite limit. So there's an infinite length interval. However, the area under the curve on that interval is actually finite. It actually adds up to 1. Which is a very weird thing to actually think about. And we'll talk about that concept a little bit more when we get to series about, well, what you're actually saying is if we were to do like Riemann sums and set up areas of rectangles and so on and so forth, you're telling me that if I added up the areas of all these rectangles, I'll actually get 1? What do you mean? I'd have to add up an infinite number of rectangles, you know, and it's kind of weird to think about it at this point. But this is actually an important interpretation, and I will actually, we'll talk about it a little bit as we move on. But yeah, the area under this curve from 1 to infinity, 1 to forever, is actually 1. Yeah.
Professor?
Yes.
Do we just say that it converges to 1 because we can't measure up to infinity?
Well, the language comes from the fact that we're using limits to approach infinity. And so yes, because we can't actually do it, we just say, this is what you're basically, when you say converges to 1, you're basically saying the idea, if we could go all the way to infinity, this is the answer we would end up with. So for all intents and purposes, you can think of it as being equal to 1, but you kind of want to be careful. What do you mean it's equal to 1? You actually added up all these areas of all these rectangles? Well, no, but I know if I could, the answer would be 1. And we'll talk about that. But that's the interpretation. Okay, just interesting. What about this one? So again, it's the same curve, but the interval is different. Right, so this is 1 to infinity, and basically what we're trying to find is the area from 0 going on to forever. Okay, so we know the area from 1 to infinity is 1, right? It's 1 squared unit. Sorry, my phone is making noise in my ears to turn off the headphones. Okay, so we know the area from 1 to infinity is 1. Let's actually figure out the area from 0 to infinity. Like what is this part of the area, right? So from 1 on this side, in other words, what's the area? I know the area to the right is 1. What is that combined with this area? So we can go and do sort of the same thing. Well, not really, because this introduces another issue, right? What is the issue here?
You have another bad point?
There's another bad point. Now 0, which was no problem before, is now a problem, right? So here, I'd have to break this into, say, and again, we can pick any number, so I'm just going to pick a nice one. And now I can use limits to approach it. Limit. We actually already know that this one goes to 1. Right, so previously found. What about the first one? Well, this is just going to be the limit as n approaches 0 from the right of -1 over x between 1 and n. So I would end up with a limit as n is approaching 0 from the right of plug in 1, plug in n. And what is that limit?
That one would be infinity.
That would be infinity. So it's infinity. In other words, we would say the integral from 0 to infinity of 1 over x squared diverges. Meaning the area from 0 to infinity is actually infinite. It's not going to add up to something finite. So here, there's infinite area. And by the way, from 1 onwards was finite area. In fact, from any point leading up to 0 is a finite area. But just to cover that gap to 0, yeah, it goes, you can't, right? It'll add up to an infinite answer. Another reason why division by 0 is so bad, right? Like it's very hard to escape a division by 0. Yeah, I can go off to infinity and it's easier to deal with than a division by 0, right? So that's something to keep in mind.
Does that mean that a vertical asymptote causes it to diverge?
Not in general. You do have to be careful and actually take your limits. I'm not making a general statement here or saying that something like this is always going to happen when you have a vertical asymptote. It's possible to not. It's possible that you rise so fast that the width you're covering compared to the height you're covering is nothing, right? Is minuscule. But here it turns out that you don't rise fast enough. So yeah, that one diverges. So diverges basically just means the limits don't exist. The limits don't add up to a meaningful answer. Let's look at this one. 1 over x squared plus 1. Now this one kind of looks like a bell curve. It's not the bell curve, right? But it actually kind of looks like a bell curve. This one is symmetric. Looks like a bell curve. And I actually want the area from 0 onwards. What is the area of that? Okay. So now if I look at this guy, 0 to infinity, bad points.
1 and infinity.
Why is 1 a bad
I'm
point?
sorry, not 1, just infinity.
Just infinity, right? So it's not like an x squared minus 1, which would make 1 a bad point. It's an x squared plus 1. That's never 0. So infinity is the only issue here. What's the integral of 1 over x squared plus 1? So now I leave the limit and focus on the integral. Integral of 1 over x squared plus 1.
Arctan.
It's arctan. No, you could do a trig, so no, you should know that by heart, right? So that's tan inverse. So this is the limit as n goes to infinity of tan inverse of n minus tan inverse of 0. What's tan inverse of 0?
Zero.
It's actually 0, so that goes away. All right, so what is, as n goes to infinity, what does tan inverse of n approach?
Doesn't it oscillate? So is there no answer?
No, tan inverse graph doesn't oscillate.
Does it approach infinity?
No. Approaches pi over 2. Okay. So the graph of tan inverse, by the way, it is something that I would expect you guys to know. So it's going to be assumed that you guys know this, so you should know this. So tan inverse has an asymptote at pi over 2. Just think of the tan graph with only the middle branch, but you reflect in the line y equals x. It looks like an S. So as you're going off to infinity, it approaches positive pi over 2. As you're going to negative infinity, it approaches negative pi over 2. That's something that you should know. The graph of tangent inverse, you should know. At least I'll expect you to know it. I'm assuming you know it. So it turns out that the integral from 0 to infinity of 1 over x squared plus 1, if I can find the area of that curve, it would converge to pi over 2. There are pi over 2 squared units under that graph. So the area under the entire graph, as you can probably imagine, is pi. Let's actually keep going. So here's a question that I want us to do, and we're going to run through it, because at the end of the day, we're going to have a theorem about this that's going to be very useful, not only in this section, but in sections that involve series, which we'll be covering eventually. So we're looking at integrals that look like 1 to infinity of 1 over x to the p dx, right? Notice that our first example looked like that. 1 to infinity of 1 over x squared, right? So that's when your p was 2, right? I want to find some sort of general idea that can apply to any such integral, right? 1 over x to the p from 1 to infinity. Okay, now it turns out that in this case, what we would do is we need to actually break this up into cases, because depending on how things, the value of p, the situation can be very different. For example, if p equals 1, I would get 1 over x. I know the integral of 1 over x is ln of x. Whereas with p equals 2, I get 1 over x squared, which the integral of that is 1 over x minus 1 over x, which is very different from ln x, right? So there are some situations where things will actually change on you here. So we have to be very careful for what p values we are choosing. So obviously p equals 1 is an important part. When p equals 0 is going to be an important part. And therefore, when it's less than 0 and greater than 0, it's also going to be important. Because if it's less than 0, if my p is negative, then I would flip it, and it's actually going to be like x to a positive power. So if p was negative 2, essentially what I'm integrating now is x squared, and that can change. So there are several important cases to consider. So let's do case 1. If your p is negative, right? Case 2. If your p is 0. Case 3. If your p is positive, but less than 1. Case 4. Your p equals 1. I want to isolate the 1 because I know at that point we turn into ln's, whereas at all the other positive points we don't. So I want to isolate the p equals 1. And then p larger than 1. So there are a bunch of cases here that we'd have to cover, right? Each of these have a different behavior. If my p is less than 0, this guy becomes a polynomial. If my p equals to 0, this is just a constant, which is the integral of that has the power rule. If my p is between 0 and 1, I'll have something else I can do that the power rule still applies. For p greater than 1, the power rule still applies. For p equals 1, it's a whole other rule, it's ln. So let's actually go through these cases and see what the answer would be in each case. And then we can come away with some sort of conclusion as to what this type of integral would behave like. Let's look at case 1. P less than 0. How can we deal with this? Well, set p equals minus k where k is positive, right? So I write p as the negative of some positive number, right? This means that your integral is that guy, which now it would just flip and become that guy. That's a polynomial. That's going to work everywhere. The only bad point now is infinity. So I take a limit and I apply the integral rules. The power rule applies. Add 1 to the power, divide by the new power. And I get that. Now k is a positive number, which means I'm taking a number, raising it to a positive power, and the base, that number n, is actually going off to infinity. What's going to happen is, well, this guy's going to go off to infinity, right? So here we get diverges. In this case. So it turns out in the case where my p is negative, this integral is meaningless. It doesn't work. Let's look at the other case, case 2. P equals 0. Well, this would mean that my integral is just integral from 1 to infinity of 1 over 1 dx. Well, that's the limit as n approaches infinity of 1 to the n. That's just x. That's n minus 1. And that also approaches infinity. So I diverges in this case too. Doesn't make any sense. Okay, case 3. Less than 0, between 0 and 1. Okay, so in this case, my I is actually equal to 1 to infinity of 1 over x to the p. I can integrate that. So this is going to be x to the minus p plus 1 over minus p plus 1. And I can plug in n. And subtract when I plug in 1. Couple things here. P is not equal to 1, so we're not dividing by 0, so that's important. It's strictly between 0 and 1. So that's good to know. Another thing, if P is between 0 and 1, so that's the first thing. Another thing is to notice that 1 minus P is actually a positive number if P is between 0 and 1, right? So if something is less than 1, I take 1 minus something that's less than 1, it means that this is a positive power. So I have n raised to a positive power, and my n is going off to infinity. So that goes off to infinity. So I diverges in this case as well. Oh, geez, we're having no luck. Okay, all right. Case 4. Case 4. This was when P equals 1. So our I would be the integral from 1 to infinity of 1 over x. This is just the limit as n approaches infinity of the integral from 1 up to n of 1 over x. Well, we're running out of space here, so this is just the limit as n approaches infinity of, well, that's ln of n, x. Apply the fundamental theorem of calculus. We would get ln of n minus ln of 1. Ln of 1 is 0. And of course, ln of n as n goes to infinity, well, that's infinity. So we diverge in this case as well. Create some space here. Okay, so I diverges in this case. Oh, wow. We've gone through 4 of the 5 cases and they didn't work. Well, we actually did an example of the last case, so hopefully this case is going to work for all possible values of p. Let's see, case 5. All possible values of p in this case. If our p is larger than 1, what's going to happen? So then our I is 1 to infinity of 1 over x to the p dx. So this is the limit as n approaches infinity of 1 up to n of x to the minus p dx. I can add 1 to the power, divide by the new power. Plug in n minus plug in 1. And let's actually look at what this limit is. Again, p not equal to 1, so not dividing by 0. Furthermore, 1 minus p is negative if our p is greater than 1. Right? Because I'm taking 1 minus a number that's bigger than 1. I'm going to get a negative number, which means here I have n to a negative power. So here my n is going off to infinity, and I have a negative power on that. So it's going to behave like 1 over infinity to a power, which we know converges to 0. And so ultimately, this limit becomes boom, converges. In this case, I converges. In fact, we know what it converges to, 1 over p minus 1. And you can actually check this with the thing that we had earlier with 1 over x squared, right? If that was plugging in p equals 2, you get the value 1 here. So if I were to integrate 1 over x cubed from 1 to infinity, the answer would be a half. 1 over x to the 4th from 1 to infinity, the answer would be a third, so on and so forth. So I can actually predict what that answer is going to look like. The important thing here, more than the specific answer, is that it's converging. So important. More so than the specific answer. So you can compute the specific answer if you want, but what is more important is that this thing converges at all. To know that there is convergence is actually a very important fact. This, in fact, leads to an important theorem, which I was trying to avoid while making space. And it is the fact that the integral 1 to infinity of 1 over x to the p dx converges if and only if p is greater than 1, which means goes both ways. If you know that this integral converges, your p has to be greater than 1. And if you know your p is greater than 1, then it must mean this integral converges. It's a very, very, very useful theorem, in fact. And it's useful for, among other reasons, we're going to use it in something called the comparison theorems, which I'm going to talk about now.
Quick question, would this theorem also be true for like any positive number on the bottom, say if it were like 2 to infinity, or would that like mess it all up?
If the number is larger than 1, then yes.
Okay.
Yeah. Remember, we actually did the case from 0 to infinity in an earlier example, so obviously that didn't work.
If it were to be, say, like 2 to infinity, it would be fine, it would converge. It's not just like solely 1.
Yeah, so if from 1 to infinity gives you a finite area, then from 2 to infinity is actually going to give you a smaller finite area. In fact, 2 to infinity would actually, for this particular kind of function, 2 to infinity is going to be a half, right? And if you go 3 to infinity, it's going to be a third, and so on and so forth. So yeah, but specifically the theorem is with 1 as the lower limit.
Would this also work if it was like 1 over x to the p plus a, like an inconstant?
Like you're saying 1 over x to the p plus a constant like this?
No, like the a would be in the denominator.
Like that?
Yeah.
Well, that is actually something that we're going to be dealing with soon, actually. Believe it or not, that's kind of where we're going. So your question will be addressed in a little while. So now we're going to look at the comparison theorems, okay? So at this point, yes, I know I didn't motivate it a lot because this is Calc 2. There is going to be no motivation, really. We're just kind of showing you how to actually compute things. At this point, just take my word for it, it's very important for us to compute integrals like this, right? They're actually useful. This is how you would go about doing it. Now we have a theorem that talks about a very specific case and when it would converge in that case, right? So now we're going to move on to talk about situations that would cover the question that you just asked. What if I had a plus a in the denominator? Okay. So in general, that can actually be quite tricky because if my P was 997 and then my A was radical 2, and you want to convince someone that, oh, 1 over x to the 997 plus radical 2 actually adds up to a finite thing, and they're going to ask you, well, how did you integrate that, smarty pants? Like, what are you going to tell them? How do you integrate 1 over x to the blah, blah, blah plus radical 2? Like, you can't actually do it, right? So it turns out that question is a lot more challenging to answer than you might initially guess, okay? So even with all the techniques that I taught you in this class so far, a general integral like 1 over x to the p plus a constant is actually something that's very tricky to deal with. And there are other situations that are tricky to deal with, right? So for example, here, I mentioned that e to the minus x squared is a super important kind of function for many reasons. The reason that a lot of people would know this from is statistics, but it does apply into other areas as well. But here's a scenario, right? So let's say I wanted to compute this improper integral, 0 to infinity of e to the minus x squared dx, right? If I know how to compute that, I would know how to find the area under a normal distribution. But how would you go about computing that? E to the minus x squared from 0 to infinity. It turns out there is a way that we can compute this. I can actually tell you what the answer would be directly. But in general, if I were to say something like 0 to 1 of e to the minus x squared, you'd actually run into an issue. The thing is, e to the minus x squared has no antiderivative. It has no antiderivative in terms of functions that we have seen so far, that we can understand in terms of elementary functions, has no antiderivative. So in Calc 1, you learned about the elementary functions, right? Polynomials, radicals, rational functions, logarithmic functions, exponential functions, trig functions. I think that covers all of them. Of course, there are inverse trig functions and whatever. But these guys are called the elementary continuous functions. And then you can have the algebraic functions, which are guys that you create by mixing and matching these functions using certain operations. So I can add two functions together, can divide them, I can multiply them, I can raise one to a power or whatever. So I can create all these various kinds of functions using these 6 infinity stones, we'll call them, right? It turns out that if your goal is to say, okay, one of these functions is the antiderivative of e to the minus x squared, it turns out you could not actually choose such a function. It's impossible to actually write the antiderivative of this function in terms of the language that you've built up onto this point, right? It's impossible to express the antiderivative of e to the minus x squared as some sort of combination of polynomials, radicals, and all those other things, right? So we say that this guy has no elementary antiderivative, okay? So in other words, if someone were to apply the fundamental theorem of calculus to this guy, good luck, you won't be able to actually do it. However, it might be very important for you to compute this integral anyway. It might be important for you to know how to find the area under this curve, or to at least know whether or not the area under this curve is finite. The actual specifics of how to go about doing something when you don't know the antiderivative we'll actually do within the next section. But to know whether or not this converges, for example, is a very important thing to know. And it's not always obvious if our function gets ugly enough. Ugly in the sense that we just don't know how to deal with it with techniques, or we know for a fact that there is no technique that exists that could give us a nice answer for this thing, right? And e to the minus x squared is such a function. There is no antiderivative. You can actually talk about an antiderivative of it, but it's not going to be something that you'd be able to write down in a finite space and have everyone understand what that means, and they're able to calculate it easily by just like plugging something in. Okay, so this leads us to the comparison theorems. Now, the power of the comparison theorems is that they allow us to talk about whether or not an integral converges without directly computing that integral, right? And that is very useful. So there are two comparison theorems that I want to cover with you guys. We're going to cover the direct comparison theorem and something that's called the limit comparison theorem. If you're using the direct comparison theorem, they just call that the comparison theorem. They leave out the direct. If you're using the other comparison theorem, you're going to get the limit comparison theorem. So there are two comparison theorems. Okay, so there's the direct comparison theorem, and then there's the limit comparison theorem. Okay. So here's what the comparison theorem says, right? So I'm not going to prove it, but I'm going to give you kind of an intuitive explanation. Suppose f and g are continuous functions on a to forever, right? So from some point on the number line to all the way to the right, my f and my g exists, right? And they're non-negative. So my f of x is greater than or equal to 0, and my g of x is larger than the f of x. So I have two functions that have this relationship. We learned in Calc 1 that the integral will maintain the inequality relationship, right? So this is something you learned in Calc 1. So if f of x is less than or equal to g of x, then the integral of f of x is going to be less than or equal to the integral of g of x, right? If this curve is bigger, the area under that one is going to be larger than the area under this one. Makes a lot of sense. Okay. However, here's something else that's nice. If you know that the integral on the right converges, let's say I told you that this guy up here converges, meaning it adds up to some number. If I were to go through the process that we were doing, it comes up with a finite number. It turns out that you can conclude from that the integral of f must also converge, right? So if the bigger guy converges, the guy up here, it turns out that the smaller guy has to converge. How do I know? Well, the smaller guy has to add up to something. It can't add up to infinity because he always has to be smaller than some finite number. So here I'm adding up areas of rectangles. The area is larger than 0, but it's definitely less than infinity. It has to add up to a number in between these, right? So it turns out if the bigger guy converges, you can know that the smaller guy also converge. You might not know what that guy converges to, but you'll know that he converges to something. There has to be some answer. I can't say that that answer will be easy to find, but I know the answer is out there. Conversely, if I were to tell you that the smaller integral diverges to infinity, and it has to diverge to infinity because it adds up to something positive, right? Because the outputs of this function are always 0 or bigger. So if it adds up and it diverges, it's going to diverge off to infinity. So if the smaller guy diverges, then necessarily it means that the bigger guy will also have to diverge, okay? And so if I know that the smaller guy diverges, I know that the bigger guy diverges. If I know that the bigger guy converges, I'll know that the smaller guy also converges. So I can tell about how one will behave by knowing about how the other behaves in two very specific scenarios. It turns out, and this is important, I'll underline this in red and probably keep it underlined. No conclusion can be made in the other cases. That's very important for you to know. Meaning, if I were to tell you that the integral from a to infinity of g of x diverges, what can we say about f? Nothing, right? F could converge, but it could also diverge as well. It could add up to a finite number and the inequality would still be satisfied. It could also add up to infinity and the inequality will be satisfied. It could diverge or converge, I don't know. Conversely, if my lower integral converges, what does that say about g? Well, nothing. G could still be converge to a finite number that's slightly bigger than or equal to the what f converges to, or it could go up to infinity. In either case, the inequality will still be respected, right? So it turns out you can't make any conclusions in any other scenarios, but in two very important scenarios, you can. And what this means is, using the direct comparison theorem, if you have an integral that you're interested in, and you have the suspicion that it's going to converge, what you can do to prove that is find some integral bigger than that you know how to prove it converges, and prove that it converges. Then you can say, well, if this guy converges, it's bigger than this guy must converge, even though I don't know to what. If you have the suspicion that this integral diverges, what you can do is find a smaller integral that diverges, and then it will force this one to diverge. Like if this one is going off to infinity, the other guy has to go up to infinity, right? So you end up in a situation that you can actually determine what's happening to one improper integral by knowing about what happens to another improper integral. And that leads to this meme right here, right? So you can actually use improper integrals to talk about other improper integrals, right? So let's deal with the situation of, okay, the integral from 1 to infinity of 1 over x to the 999 plus radical 2. Like, I don't have a technique for that. Well, I do technically. Let's say, because substitution would work there. Well, no, substitution wouldn't work there. So let's say I have the integral from 1 to infinity of 1 over x to the 999 plus radical 2, right? Does that converge? And you're like, how am I going to actually do that integral? Well, you don't. What you can do is just ignore the square root of 2 and just deal with the 1 over x to the 999. I know from the theorem earlier that that's going to converge. And so I can know that that integral that I'm just talking about will converge, right? So, so let's throw out an example here, right? To deal with the question that was earlier. If I have the integral of, say, 1 over x to the 999 plus radical 2 dx from 1 to infinity. Converges? Well, what I can do is look at this integral, 1 over just x to the 999. 999. Now that one I know converges. This converges by above theorem, since my p is larger than 1. And notice what is happening here. If I look at the integral of 1 over x to the 999 plus radical 2, and I look at the 1 over x to the 999, how would you compare these in terms of inequalities?
The one on the right is bigger because it has a smaller denominator, so it's being divided by a smaller number.
Right, so this guy is bigger, which means if I throw integrals on these guys, this integral over here on the right is bigger. And I know, so if I throw on integrals here, I know this converges. So I have found a g of x to compare to the original integral. So if I had the x to the 999 plus some constant a, and that constant was very difficult for me to deal with, I don't need to deal with it. What I can do is ignore the constant, see the relationship that I have afterwards, and see if I can apply a comparison theorem. And in this case, I could. So instead of doing the integral of 1 over x to the 999 plus radical 2, I don't need to know how to do that integral. I don't want to know how to do that integral because it's going to take some serious partial fractions that I'm not ready for and no one's ready for. So what I do is ignore the radical 2. Notice that I get a bigger integral that I know converges. How do I know converges? Because it's this theorem with p equals 999. So I can know that the upper integral converges, which tells me that the lower integral converges. So this would mean, call this I converges. And notice that I can know it converges without actually doing the integral. Like what does this add up to? No idea. I have no clue. It adds up to something though. And I can even tell you what that thing would look like. It would add up to 1 over 998. It's something less than or equal to that. I can tell you that. But more than that, I can't really say, right? So I can actually know about what this integral is going to do based on what the upper integral is going to do. So that is called the direct comparison theorem. If I know a bigger integral that and it's actually important, let me actually underline this as well. Them being greater than 0 is actually very important. Being non-negative is important. Because otherwise things could go off to negative infinity and mess everything up. Being non-negative is also important. Let me emphasize that.
Professor?
Yes.
How do you know that would you know that g of x is greater than f of x when you have I don't know, 1 over x squared plus 5x, and then 1 over x squared minus 3x plus 7? How would you know?
That leads us to the next comparison theorem. But in general, for this one, it's easy to actually tell because it's clear that the denominator on the left is larger than the denominator on the right. But yeah, you bring up an interesting point. What if it was x to the 999 plus a whole bunch of other stuff, and I wanted to compare it to 1 over x to the 999? How would I actually know that the x to the 999 is bigger or smaller? Or even worse, what if I know that the x to the 999 is actually smaller than it? Can I make any conclusions? Well, no. This leads to what's called the limit comparison theorem. So it turns out that why this guy is important, we can use this even if we don't know the inequality relationship. So the questions you're asking are very logical. So because they spoke of it, we eventually get there. So yeah, how would you integrate the 1 over x to the p plus some random constant? Comparison theorem. You can tell that it will converge by a comparison theorem. Well, what if it's a weird kind of construction where I can't tell if the g is bigger than the f or the f is bigger than the g? Well, the limit comparison theorem can deal with that situation because now you don't actually care about who's bigger or who's smaller. So the limit comparison theorem says f and g are functions that are continuous on a to infinity. And let's say when you divide them, f of x divided by g of x, and you take the limit as x approaches infinity, you get a number that is positive. Then it turns out that both integrals will actually do the same thing. So they'll either both converge or they'll both diverge. So if you're looking at something like, well, I have some examples here. So example, when we don't have an inequality relationship or direct comparison is problematic. And I have some examples, which of course you guys will work on and we'll deal with next time. But let's actually just give an example of this idea. So example here, let's say I asked you about 1 to infinity of 1 over x to the 999, but now I go minus radical 2. What you'd want to do is you'd want to compare to the integral from 1 to infinity of 1 over x to the 999. Now you start to worry about how these guys relate to each other. We know this converges. How do these two relate to each other? Who's bigger, the guy on the right or the guy on the left?
The guy on the left is bigger because it has a smaller denominator.
Right. So I can throw some integrals on these guys. But notice that direct comparison does not apply. Right? Direct comparison applies in two very specific scenarios. If the larger integral converges, or if the smaller integral diverges. Here, I'm in a situation where the smaller integral converges, tells me nothing. So what you can do in this case is use limit comparison. Essentially, what you can do is you can take the limit, right? So let's say your f of x is the 1 over x to the 999, and your g of x is the 1 over x to the 999 minus radical 2. Then, if you take the limit as x approaches infinity of f over g, what would you get as the answer? One, right? Again, this is from Calc 1. So you do have to know about limits, right? And you have to go back over Calc 1, remind yourself of L'Hopital's rule, all those stuff, ratios of polynomials, how they behave for limits at infinity. If the highest power is the same on top and bottom, you go to the ratio of the coefficients. So it's 1, right? Which is greater than 0, which means the integral of f and the integral of g behave the same way. And that would mean that the integral I converges, because I already know that the integral of f converges. So again, it's a situation in which I didn't actually compute the integral, but I can know whether or not it converges. I know there's a meaningful answer out there, and then I could approximate it with computers or something else, which we'll talk about next time. But at this point, it's very important that we're able to compute improper integrals, but not all integrals are very nice, or there might be impossible for us to integrate by traditional means, or they just might be too difficult to integrate by traditional means. And so what we do is we compare them to easier integrals. And these two are theorems that tell us how we can compare things to easier integrals. If I know how the inequalities are changing, the direction in which the inequalities are going, and all the functions are non-negative, I can apply the direct comparison theorem in two specific scenarios. If I don't have that, then the limit comparison theorem can probably help me out. But of course, with the limit comparison theorem, you'll need to know how to take limits. So it's an extra step. You only kind of use it if you have to. But that's kind of wrapping up. Here are some examples for you guys to try. Be very useful. And I will leave these in the notes. But yeah, right now we're gonna wrap up there. So improper integrals. It's when we have infinity in our limits or our function is not defined. We can deal with these by breaking up around the bad points so that there's only one bad point per integral. Take limits to approach these bad points. If all your limits add up to a nice finite numbers, you can add them up and it'll converge. If any one of your limits mess up, the whole thing diverges. We can actually use theorems to talk about when improper integrals will converge in some cases without actually doing the improper integrals. These are the comparison theorems, for which knowing this theorem is super useful, because it turns out that 1 over x to the p is very often a nice thing to compare to. So we'd have the comparison theorems in that case. Right, so try these examples. We'll deal with them next time, but for now, that's all the new ideas we want to cover today. So improper integrals, you need to know about integration. You also need to remember your limits from Calc 1. So be aware of that. That being said, we can wrap up there. Okay.
Thank you.
All right, that's it. Have a good night, everyone. Good luck tomorrow. And I will yeah, that's it. I know I have office hours with one of you, so I'll be sending you the link shortly. And that's it. I will see you guys in the next one. Ciao.